Welcome to another video from Lockdown Electronics with me, Bill, and this time this is a bit of a beginner's video in the sense that we're going to look at some simple circuits that you can easily build on a breadboard, and we're going to be exploring those circuits with a multimeter. This is the Kaiweets HT118A, a bit of a review up there if you want to have a look at it, and we're going to use this to see if we can discover what's going on in those circuits, and in the process learn a little bit more about electronics. So let's go and do it. Oh, and you definitely don't need an oscilloscope. Okay, here I've got a circuit set up on my breadboard. Ignore these two, we're just looking at this little segment at the moment, and this is the 555 timer chip. Here's a circuit diagram of what's laid out on there, and the 555 timer is probably the most famous integrated circuit ever produced. They've been making them since 1972. There must be millions and millions in the world, and still today it's a very handy little circuit. It allows you to produce pulses in a very straightforward way, and the way it works is the chip itself in this configuration is running in what we call astable mode, free running, and the two resistors and the capacitor form a circuit which controls how long, or the frequency if you like, or how long the pulse is, and it also controls the duty cycle, since the output is square wave. So we've got the circuit configured there. So let's just, here's a close-up just so you can see how it looks on the breadboard. Okay, there's the two resistors and the dividing that form the voltage divider, and also the capacitor there controlling the time, and this is the decoupling capacitor at the bottom. So okay, first thing to check then, we are powered up, is let's check if we've actually got supply voltage, which should be 5 volts. Yeah, so there we've got with 5 volts, so presumably this should be working then. So let's see if it is. The output actually appears here on pin 3, so that little yellow link there takes us across from pin 3, so let's see what we can see there. Well, it says 2.3 volts, that's on DC, so there's certainly some voltage there. Let's go on to AC volts and see what it's telling us. Well, it says there's 2.4 volts AC, and the frequency readout at the top appears to be saying the frequency is about 245 Hertz, something like that. So yeah, that seems like it's working. Let's just have a look what's happening in the area of the circuit that is involves the actual control, where the capacitor does its work. So there we've got AC voltage of about 5.48. Let's just see what we get. Same place for DC volts. About 2.5 DC volts. So yeah, that seems to be working okay. Although right now I'm not absolutely sure. Now, if it really is, let's go back to AC volts. If it really is 250 Hertz, as that appears to be saying it is, that's an audible sort of tone. Sorry, you can see the meter a little bit better like that. That's an audible sort of tone. So what I've got here is a cheap and cheerful Chinese cable tracer, and this is designed to help you find cables that are buried in walls, and there's another part to this which injects a signal. But what it essentially is a very sensitive bit of a coil there, and an amplifier and a speaker. So if I switch on, you can hear it humming, probably, just about. So let's move it near to the 555. Yeah, there's a very strong tone near the output, and also in this part of the circuit here, so there's definitely something happening. So if I just do that again and I take the power off, yeah, that's definitely something that's occurring in the circuit. When I take the power away, tone just vanishes. So it's definitely working, and we know we've got a couple of voltages here, and we've got a couple of voltages there, so that's good. What have we learnt? A little earlier in the video, you might recall I said you definitely don't need an oscilloscope. That might have been a bit reckless. I mean, you don't need an oscilloscope, but they're actually awesome bits of kit, and actually these days they're not stupid money. So do we need an oscilloscope? Is it going to tell us any more than we've already discovered using the instruments that we've already used? Well, actually, yeah, it just might do. An oscilloscope really is a form of meter. It's not, well, digital oscilloscopes are a bit like a digital multimeter, and analog oscilloscopes are a bit like an analog meter, in the sense that an analog meter gives us a measurement using a moving needle, and the digital instrument gives us a reading using numbers and sometimes a bar graph. And an oscilloscope sort of does both of those things. Old-fashioned analog oscilloscopes are similar to your analog meter, where the oscilloscope measures volts and plots that measurement against time on a graph. And a digital scope also does that, but because the data that it's taken in is now in the digital domain, it can do maths on that, and it can give you measurements like frequency and voltage and things like that. So let's see how much an oscilloscope can tell us that we don't already know from using our meter. Okay, so here's the same circuit. Still got the meter here, but now I've got my fairly ancient but very nice analog oscilloscope. It's a single channel analog oscilloscope. It was about £65 off eBay, and I've got it running there. I've got it set so that each of these squares here is equal to about 2 volts, because the thing about an oscilloscope is it's really just a voltmeter. Simple as that. Now, you recall the first measurement I made, which I'll just do again. I checked the supply voltage, and that gave me an answer of, well, 5.06 volts roughly. So that's 5.06 volts. So let's see what the oscilloscope makes of that. I've got the earth of my oscilloscope probe connected to ground, so let's just check the supply rail, and straight away you can see that the line has jumped up. It's still straight, but it's gone up 1, 2.5 squares, so 2.5 times 2 is 5, so there's your 5 volts. Now I've got the oscilloscope set in DC coupling mode here. I'll come back to that a little bit later. Quite often you can set an oscilloscope in AC coupling mode, and if I put the probe onto the 5 volt supply there, it does momentarily jump, as you can see. Well, it does the first time, just let the charge dissipate. But now, attached to 5 volts there, it says nothing. And certainly that's not the case, because if we go back to the multimeter, there definitely is 5 volts, yet the oscilloscope doesn't appear to be saying there's anything. So that's something to be wary of. So we need to be in DC coupling mode there, which allows the oscilloscope to read DC voltage. Okay, the next thing we measured was the actual output from the 555. So we connected negative to ground, and then we probed the output, and it's given us 2.5 volts DC, and then it's also giving us about 2.2 volts AC, but it doesn't actually read anything for frequency, so not really sure what's going on there. Maybe it's about 2.5 volts. So let's see what the oscilloscope makes of that. Aha. Interesting. So we appear to have a square wave, and it's a very pronounced square wave. And here you can see where an oscilloscope certainly wins, in the sense that the meter on AC is managing to read, and as you can see here, it is about 4 point something volts. Remember, that's I've still got it DC coupled, so there is, it doesn't appear to be any DC. If I ground the oscilloscope, you can see that when I come back to measuring that wave, the baseline is still the same as the bottom of the wave there. So yeah, we've got just over 4 volts of pulse there, 4 point something, and it's nice and clear square wave. I've got this set to 0.5 milliseconds per division, so it's just under 1 millisecond for 2 divisions there. So if you want to go away and do the maths, you can work out what the frequency is there. We'll come back to that in a minute. So yeah, we've clearly got an alternating voltage there, square wave, but the meter has struggled to make sense of that, and it certainly wasn't giving us a frequency reading, you might recall. So if we go back to DC coupling, the display moves, but actually the height of the wave doesn't change. So that's telling us that this voltage is rising from 0 up to 4 point something and back again. Those are its pulses. Okay, now we also made some measurements near the dividing bridge and the capacitor. So let's just remind ourselves what they were. We're back onto DC there for the meter. So we'll connect the DC lead to ground, and we'll just probe the area of the divider there on pin 2, and it's saying about 2.5 volts DC. Turn that to there, AC, and we'll do the same thing again, and we're sort of getting, we're getting about 0.5 volts AC, so that's sort of a bit weird. So wonder what's going on there then. Let's see what the scope makes of that. We're still in DC coupling mode, so let's remind ourselves there are the output pulses, and here is that pin 2 on the 555. Aha! So we've got what looks like a ramp wave. The sides aren't quite straight, and significantly, if we just ground the trace for a moment and then take the ground off while I'm on there, you can see it rises up from the baseline. So some of that voltage is DC, about 2 volts actually, but some of it is clearly it's a changing DC voltage, and what we've actually got here is, if you like, an alternating voltage and alternating current and direct current superimposed on each other, and of course they can exist in a circuit together, and you can use capacitors and coils and resistors to filter out the bits that are needed or not needed. So if I just put the scope into AC coupling and just turn up the sensitivity a little bit, so you can see the shape of those waves, what you're actually seeing here, this is the capacitor charging up, discharging and charging up again. So you're actually seeing the capacitor doing the work. And if I go back to the output pulses, this is going to be way too powerful for that voltage range. You can see you've got just under 2 divisions per wavelength, if you like. So from the top of that one, you've got 1, 2, 3, about 4 divisions for a complete wavelength. So let's go back to our capacitor trace again, and we'll just turn the sensitivity up, and sure enough, you've got about 1, 2, 3, 4. So it's the same frequency, and this is a single channel scope. A dual channel scope, you could display both traces together, so we'll have a look at that in a minute and what that tells you. But yeah, as you can see, the capacitor doesn't charge up in a linear fashion and doesn't discharge in a linear fashion, but this is what is controlling the triggering of the 555 to output those pulses. So if we go back to there, and just remind ourselves. So what we've got in AC coupling mode, we can just see the AC voltage, but if we now DC couple the scope, it shows us the DC component as well, and that's the thing that the multimeter is never going to uncover. Although the multimeter itself was telling you, yeah, roughly what that voltage was, and it was also telling you roughly the average of that voltage too. So it actually tells us quite a lot, and the scope gives us some other significant information. And of course the very obvious thing the scope does tell us is that our 5/5 timer is indeed outputting pulses. So there you go. Okay, so now I've got the same circuit still running, and I've now got it attached to my Hantek 2D72, which is a two-channel digital oscilloscope, and channel 1 is the yellow trace here, and you can see we've got the same square wave that you were seeing earlier on the Hameg analog scope, and you can see there's a little bit of noise on that starting pulse. That's got more to do with the way I've got the breadboard set up than anything else. It is not as pronounced as that in reality. And the second channel I've got connected to the resistive capacitive bridge, the triggering part of the circuit, and I've currently got that channel connected to ground, so it's showing you where the baseline is. So let's now move that from ground coupling to AC coupling, and first thing you get is you get that ramp wave as we saw before, and you can see now, and this is the advantage of a dual channel scope, you can see its relationship in terms of phase or time, if you like, to the output, and as you can see it is in synchro with it, so it's definitely connected to it. Now we're only seeing the AC component there, and so if I now change the coupling yet again to DC, you'll see that jump up, and it's hopped up there from the baseline, so that's the 2 and a bit something volts of DC that are part of that circuit there, and then that's the charging and discharging of the capacitor, which we were talking about earlier. So that gives you a much, well, even more information, because it allows you to compare what's going on with the wave. And in fact, if I move the trace up, you can see the relationship of the capacitor charging level to when the pulses stop and start. So that's a digital scope. The other thing that a digital scope is good at, I'm going to just turn off channel 2, and now I'm going to ask it to come up with measurements. Let's just go to measure and enable. So now it's giving me stats on the channel 1 input, and it's telling me there that it's about 535 hertz, so about half a kilohertz or so. And that's the, I could have measured the time divisions on the analog scope and done the maths. This is doing the maths for me. So you're getting an idea of the frequency there. And remember that because it's a square wave, the multimeter, which would actually read, if it was a sine wave, it would actually read it no problem and tell me the frequency, but it was struggling because it's a square wave, and so there's a great deal more energy there than there would be in a sine wave. Also, of course, it's not really crossing zero as well, which is a bit confusing for this poor old multimeter. So there we go. That's a digital scope with 2 channels. Okay, hopefully you've found that useful and seen the difference in the types of information we can get from a multimeter and from an oscilloscope. They're both useful, they're both telling us about voltage, but they both give us information in a very different way. Now, I did earlier suggest that you definitely don't need an oscilloscope. I think maybe I'll scrub the word definitely and just say you don't need an oscilloscope, but boy, they're handy. And one of the most powerful things I think about an oscilloscope is that it allows you to see what's going on inside the circuit, and we human beings are very visual people, very visual characters. We take on information visually, and I just think it allows you to make connections up there between what you've read about and what people tell you the circuit's doing and actually what's happening to the voltage. Now, you've seen me using a fairly ancient analog oscilloscope that was about £65 off eBay. The Hantek 2D72 is more expensive, but they do slightly lower bandwidth versions that you can get for just over £100. But you don't even need to spend that much. If you look at this video up here, which talks about this little beastie, this is the DSO138mini, and this is a kit that you can buy to make your own oscilloscope, and this is more than capable. It's a single channel scope, it's got AC and DC coupling, it'll handle up to 50 volts on the input, although I think I'd probably be not too happy feeding 50 volts into it. I'd probably put a lot less in, but that's certainly capable of showing you everything you've seen on those other scopes. And I think it was about £16 in the UK, that kit. So as I say, have a look at that video I made about it, because that is a nice cheap way of getting you that visual information, and you get to learn a bit by building a kit along the way. So hope that's made some sense. If you've liked it, please click the thumbs up. If not, you can click the thumbs down. Either way, it'd be really good if you could subscribe. That'd help me. Thanks very much for watching. See you on the next one.